So now we do introduction to vector fields. And we start with this motivating question. How would you mathematically represent wind patterns or water currents? Or how about the force of on an electron in the presence of a magnet? So for you, I've got some nice pictures. So the first one is actually from the NOAA, and you can see it's a depiction of water patterns on Earth. And the second one, now I hope, so I did this in science class when I was in high school. I hope y'all did it the same. It's great. You take these iron filings and you take a piece of paper, put it on top of a magnet, you drop the iron filings on the sheet of paper, and they all line up like this, and it shows you the magnetic field. Third one, we've got an image of what's going on with the wind patterns. So, what are we talking about mathematically here? For wind and water, what you want to do is measure the velocity of a particle at any point. So that gives you what's called a velocity field. So with the magnet, you can measure the force exerted on a charged particle at any point, and that we call a force field. And either way, at every point in space, there's a magnitude and a direction. So what you have is a vector field. So a vector field is a function which takes a point in Rn, or a region of it, and assigns a vector in Rn. Now, for our purposes, of course, we're going to typically work in R2 or R3. And in each of these pictures, you can see vectors being drawn at just various points. So that's the application or the idea. What would this look like as a formula or a notation? So we can write the formula in this way. So in R3, you'd say vector field F. So we use capital F with either bold or with the arrow. And we can write it like this, either as function P of XYZ times the I vector plus function Q of XYZ times the J vector plus function R of XYZ times the K vector. Or just in general, sort of short, quick notation, the vector PQR. And from now on, when we use capital P, capital Q, capital R, we're going to understand that refers to these functions, which are components of a vector field. So that's what P, Q, and R stand for. Capital P, Q, and R stand for from now on. Okay. So here are some examples. So on the left, we've got an example of a two-dimensional vector field. So notice that each component is its own function of 2 dimensions, so function of X and Y. And at any point, you can plot what the vector would be just by plugging it in. Same thing on the right, but on the right, it's for something 3-dimensional. So now let's do a calculation by hand to see get a better idea, further idea what this means. So for this vector field, first component y over x, second component x squared y plus sine of pi x. Find the vector at the point for -2. So what do? All we do is plug it in. So we say vector field F at the point for -2 equals, so plugging it in, I'm going to get -2/4, and then 4 squared -2 plus sine 4 pi. And then that works out to -half. And if you calculate, -32. So as a picture, what does this look like? Let me draw that over here. So what this tells you is that when we're at the point for -2, which let's say is approximately right here, From that point, the vector is -½ -32. So, and I'm going to approximate drawing that point in. So something like that. So now, in particular, notice that this is it's very important to note that every single point in our space has its own vector. So previously we said, oh, just throw the vector up there, it doesn't matter where it is. Now every point has its own vector. So it's tremendously important what the point is, or we sometimes call it the base point. And this is how we make a vector field. Okay, now we've actually previously talked about a particular type of vector field. So the sort of thing such that at every single point we have a specific vector. And that vector field was the gradient vector field. So given for a given function f of xy, at every point xy, you get a particular vector. And of course, gradient of f, so df dx, comma df dy. Now this is a very, very special vector field because it has very special properties. We know special properties of the vector. In this vector field, every vector points in the greatest rate of change of the function, and the magnitude is the maximum rate of change. So just as a reminder, for this vector field, for this function, let's figure out what the gradient vector field would be. So our vector field, big F, is just the gradient of function f. And that's just df dx, so 2y e to the xy, and df dy, 2x e to the xy plus 2y. So there's the gradient which you've calculated before, but now we can also think of this as the vector field, and that is now graphed on the right. So of course, this is a very, very special vector field. We can just make, for a vector field in general, we can just make any function we want. This is a special vector field called the gradient vector field, which is calculated in a very specific way. So vector fields are super, super important. In physics, specifically, and then kind of throughout STEM as well. So here are some examples. A fluid velocity field, mentioned this before. So it's the velocity vector of a fluid at any point described by the vector field F. Another kind of important one, the gravitational force field. So we kind of know what this means, but let's talk about where it comes from. Okay, so Newton's law of gravitational attraction says the force between two masses is this. So the force F equals gmm over r squared. So that's big G. That's a known constant. We'll talk about the value. I'll give it to us later, but it's some constant. Little m and big M are the two masses measured in kilograms, and then r is the distance between them. We'll measure in meters. So that's just, notice that this is just the magnitude of the force between two masses. Now, obviously, the force also has a direction. So let's talk about what that would be. So if we imagine that mass big M is fixed at the origin, 0, 0, and mass little m is at the point x, y, which is just our position vector r, then the force on mass m is from r to the origin. So from r to the origin, just do b minus a. So 0, 0 minus xy. So the direction vector is negative x comma negative y. In other words, just negative of the position vector r. But of course, we just want to describe the direction, so we need to divide by its magnitude in order to make a unit vector. So the unit direction vector is just negative r vector over the magnitude of r. And remember, it's a common notation to write it just not bold, no arrow, represents just the magnitude. So we now have the magnitude and the direction of this vector, and therefore we get that the gravitational force is this vector described by the vector field called the gravitational force field. So it is vector field F equals, we got to take GMM over R squared and multiply it by our direction vector, and we unit direction vector, and we get negative GMM over, that's the magnitude of R cubed, times the vector R. And there's your formula for the gravitational force field. Okay, next, electric force field. So, if you have two charges in space, Coulomb's law of attraction says that the force between the two charges is this. The magnitude of the force is KQQ over R squared, where K is some known constant. Little q and big Q are the two charges measured in coulombs, and R is the distance between them measured in meters. So this should look pretty familiar from what we just talked about. So once again, the force has a direction. Now there's a little twist. Assume that charge big Q is at the origin and charge little q is at some point in space xy. There's a little twist because we know that forces between charges, the force can either be an attraction force pulling them together or a repulsive force pushing them apart. So here's how we include that. Notice that if charges have the same sign, then the force will push them apart. Same sign means their product is going to be positive. And if charges have opposite sign, they're going to attract. And of course, if they have the same sign, then their product must be negative. Sorry, opposite sign, the product must be negative. So in that case, the force would be toward the origin. And then once again, just like we said before, the unit direction vector is going to be position vector r divided by its magnitude. And it's going to be either positive or negative. So we now have the magnitude and direction. So now we have the electric force field. And this is F equals KQQ over R cubed times the R vector. And again, notice that if they have opposite, if the charges are opposite, their product is negative. So that whole thing will be negative, meaning it's pulling in toward the origin. And if they have the same sign, then the product will be positive, and it'll be pushing out toward the position or out into space, away from the origin. Okay. So those are some basic examples of vector fields and some quite important vector fields in physics. So one final comment. We mentioned that we had already met a certain type of vector field, which was the gradient vector field. It turns out that the gravitational field F, which we just described, is actually a gradient vector field. Now, if something is a gradient vector field, what does it tell you computationally? It tells you that there must be some function F so that you take its gradient and you get this vector field. So the question is, what is that function? So I'm going to give it to you right now. So f of xy equals GMM over R. And now we're going to prove, so we're going to check or prove that that is the function such that when you take the gradient, you get the vector field. And for this calculation, remember that that little r is a magnitude, so it's the square root of x squared plus y squared. So let's check it out. So first of all, let's write f in coordinates. So it's GMM over x squared plus y squared to the half. So let's rewriting it out because we're about to take derivatives. Looks like this. And now let's calculate the gradient. So the gradient of function f is, first take derivative with respect to x, you get GMM times negative half. So GMM is just constant here, times negative half times x squared plus y squared to the negative 3 halves, chain rule times 2x. And then again, very similarly for df dy. So you get this. Now let's simplify the whole thing. So what happens? Notice that the 2 and the 0.5 will cancel. Next, the GMM and the negative sign, that's all a constant. We can factor that out. And then x squared plus y squared to the negative 3 halves. First, we can flip that to the denominator. And second of all, notice that x squared plus y squared to the half is just r. So that whole expression is really just r cubed in the denominator. So that's a That's a scalar. It's not a constant, but it's a scalar, and we can also factor that out. And what's left is xy. But what is xy? Xy is just our position vector r, and that gives us our final answer, which is previously exactly what we said the force field was for gravitation. So, some terminology to connect these things. So, if we know that we have a function little f and a vector field big F, and the gradient of function f is vector field f, then little f is called the potential function of the vector field big F. I'm saying little f and big F's to distinguish. Okay, so, and vector field f is called conservative. So just one comment, in physics, the convention is we take the potential function p to be negative of this function. So therefore, you'd have negative of the gradient of p equals the gradient of f equals our vector field f. So for our purposes, we're going to talk about the potential function being f, although in physics, they'll talk about the potential function being p. Just remember, it changes by a sign. And very importantly, we're going to deal with this going forward. Little f, which is the function, big F with the arrow is the vector field, and then big F, no arrow, which is the magnitude of the vector field. Those three things are different objects. Unfortunately, it's all the same letter F, but we're going to deal with this, so you'll get used to this. But keep in mind going forward that those three things are different objects.